So next up for us is going to be Chapter 5, Oxidation and Reduction Reactions. Probably 3 to 4 segments here. Uh, Continuing on with our aqueous solutions. So remember, all these reactions would still be in aqueous solutions. So all that information about molarity, balancing, all that stuff is going to be still going strong here. So in this chapter, we're going to look at the definition of oxidation, reduction, what oxidizing agents are, what reducing agents are, and of course, calculating oxidation numbers. From there, we're going to look at how to balance oxidation and reduction reactions. There's several different methods. We're going to explore a couple of them. We'll look at how acids react with metals, and then we're going to look at what's called the activity series. Now, you should be able to get yourself a copy of the activity series. You're going to want to have that, especially when we go into assessments. That would be something I would give you on an exam. It's not something I expect you to memorize, but it's basically a listing of what metals can replace what metals. And again, we'll go through that in these sessions here. Then we're going to learn about the reaction of oxygen with organic compounds, metals, and nonmetals. So basically combustion. Combustion is a subset of oxidation and reduction. And then, of course, here comes our good old friend, stoichiometry, how to perform the calculations using the stoichiometry of now oxidation and reduction reactions. So, oxidation and reduction, what's going on here is the electrons are going to be transferring. Okay, and usually it's like metal to metal. So what we'll see is an iron plus 3 becoming an iron plus 2, or an iron plus 2 becoming an iron plus 3. So far, when we've looked at reactions, if we had iron 3 in the beginning, we would do some sort of metathesis, and we'd still have iron 3 in the end. And so now what we're going to see is that's not always going to happen. What we're going to have is an electron transfer. So electrons transferred from one substance to another. Originally, only combustion of fuels or reactions of metal with oxygen were known to do this. It is an important class of chemical reactions because it actually turns out that it happens in a lot of biochemistry systems. They're also called redox reactions to emphasize that the reduction and oxidation must always occur together. So again, we'll call them redox. It's never just one or the other, it's redox. Okay, and we'll learn about oil rig as well. So how to keep track of where the electrons are going, what's being reduced, and what's being oxidized. So in an oxidation reduction reaction, two things have to happen. First, we have to have oxidation, which is going to be the loss of electrons. Okay, so oil, oxidation is loss. Okay, so oxidation, you're going to lose the electrons. So sodium going to sodium plus 1 electron would be an oxidation half reaction. Now obviously the electron can't exist out there by itself, and that's why these reactions come in pairs. So since we now have that free electron, what we're going to need to have is a reduction. Someone's got to gain that electron. Something's got to happen so that that electron is not sitting out there by itself out in the nether, because that cannot happen. And so here we'll take chlorine gas, Cl2, and we'll add 2 electrons, and that will produce 2 chlorides. And that would be our reduction half reaction. That would be Rig. Okay, reduction is gain. So oil, Rig. Oil, oxidation is loss. Rig, reduction is gain. It's almost like it's backwards in our heads, right? We think of when we gain things, that would be a positive, but in this case, when we gain it, what we're gaining is the electron, and so it's going to be a negative charge overall. So if we see the charge going down, then we're gaining electrons. That's reduction. If we see that charge going up, right, so we went from sodium is 0 to plus 1, it went up, that is going to be oxidation, right? So we've lost electrons. Your net reaction in an oxidation reduction is 2 sodiums reacting with that chlorine gas are going to produce 2 sodium ions and 2 chlorides, which of course will end up making our table salt. So oxidation and reduction always have to occur together, and you can't have one without the other. Okay, so oxidation and reduction reaction then. You'll hear the terms oxidizing agent and reducing agent. So an oxidizing agent is a substance that accepts the electrons. So basically, this is the thing that's going to cause the oxidation. So again, that's the material that's going to cause the oxidation to take place. Okay? That means it's going to accept electrons from another substance. This will be the substance that is reduced. So if we look back at our previous reaction, we had sodium and chlorine. Chlorine was the one that accepted the electrons. That means it would be the oxidizing agent. So it's not actually undergoing oxidation, it's causing the oxidation in something else. So the chlorine plus 2 electrons was reduced, and so it was the oxidizing agent. Now, the other half of that means that we'd have a reducing agent. There's a substance that had to donate the electrons. That would be our reducing agent. So it's going to cause the reduction, right? So it's going to release the electrons to another substance. This is going to be the substance that is oxidized. So if the chlorine was the oxidizing agent, then sodium was going to be our reducing reagent. All right, so redox reactions are very common, right? And for my EE people, here you go. That's your batteries, right? You have a cathode, you have an anode, positive end, negative end. So cars, flashlights, cell phones, computers, all those batteries are all based on redox reactions. The metabolism of food. So those of you that are going into some sort of medical profession and you want to go to med school or dental school or PT school or whatever it may be, metabolism of food. And then of course there's good old-fashioned combustion. Now we can also deal with chlorine bleach, right? Especially this time you got COVID going on. Chlorine bleach, you can use dilute sodium perchlorate solution. This is going to clean through redox. Okay, so it's going to be a redox reaction that's actually doing the cleaning. And it's going to act as an oxidizing agent, which means it's going to reduce everything around it. Okay, it's going to destroy the stains by oxidizing them. So it's going to reduce and oxidize the stuff around it. I think I mixed that up, but it's going to be the oxidizing agent. So it is going to reduce and it's going to oxidize the stuff around it. All right, so how about fireworks? Fireworks displays, we're going to take magnesium plus oxygen. We're going to produce magnesium oxide. And of course, it's going to give off bright white light. And that's going to give us our fireworks display. So the oxidation half would be the magnesium. Magnesium is going to go from Mg to Mg2 plus. For that to happen, 2 electrons have to be pulled out of there. And so we can see we're going to have a loss of electrons, which means it's going to oxidize, which means it's going to be the reducing agent. For the reduction half, we have O2. O2 is going to gain electrons to become O2 minus, right? And so it's going to gain electrons, which means it's the oxidizing agent. All right, so how's this all going to work? Well, I'm going to give you a reaction, and you're going to tell me which species functions as the oxidizing agent in the following oxidation reduction reaction. So, is it the platinum, the zinc, the platinum ion, or the solid zinc? So which one is going to act as the oxidizing agent? So we can see zinc is going to go from 0 to +2. That means it's going to be what? Oxidized, right? Because it's losing electrons. The platinum is going to go from 2 plus to 0. That's a reduction even though we're starting at a plus, right? So it's +2 reducing to 0. And so the oxidizing agent then should be the platinum. All right. Which species gets oxidized in the following reaction? And a lot of times with these questions, you just got to take your time and figure out what's being asked. Okay, so that's where the confusion will set in. Which species, in other words, which one of these items is being oxidized in the following reaction? Is it the silver ion, the zinc ion, or the zinc? And of course, none of these is probably a throwaway answer as it was in the last one, right? We have all 4 things listed here. Something's going to have to get oxidized. So the silver is going to go from +1 to 0. That's reduction. And zinc is going from 0 to +2. That means that's going to be oxidized. All right, so hopefully you're getting these down. In the following reaction, which species is the oxidizing agent and which gets reduced? So now we have hydrogen plus ion reacting with manganese to give us manganese ion and hydrogen gas. In the following reaction, which species is the oxidizing agent and which one is getting reduced? So H plus is going to 0. That's reduced. Manganese is 0 going to +2. So that means the manganese should be the oxidizing agent. Is that right? Or did I get it backwards? So which one's being reduced and which one is the oxidizing agent, or are they the same? All right, so hopefully you realize they are the same. So H plus is the oxidizing agent, and that is what is being reduced. Okay, so don't get confused by those terms. We might have to go through that a few times. All right, so guidelines for reduction reactions. Oxidation and reduction always occur simultaneously. So it doesn't matter which half you write first. It doesn't matter if the metal that's going to be reduced is first and the metal being oxidized is second, or flip them. It's not going to matter because it's all happening at the same time. The total number of electrons lost by one substance has to equal the total number of electrons gained by the second. So we've already looked at balancing reactions by mass. Now we're looking at it by charge, and these still have to balance out. Okay, so if I lose 10 electrons, somebody has to gain 10 electrons. That's just the way it is. We can't have free electrons floating around. For a redox reaction to occur, something must accept the electrons that are lost by another substance. So if we don't have a species there that can accept the electrons, then the oxidizing agent can't release its electrons, right? That brings us to oxidation numbers. So again, this is going to be a bookkeeping method. It's just a way to keep track of your electrons. So not all redox reactions are going to contain O2 or ions. So what we have to do is just simply keep track of the electrons. Covalent molecules and ions are often going to be involved. So in other words, we can have methane, SO2, manganese, permanganate, things of that nature. Defined by sets of rules, of course. There's always rules, and we're also going to see that there's going to be exceptions to the rules. How to divide up shared electrons in compounds with covalent bonds, often whole numbers, but they can be fractions. Well, change in oxidation number of an element during a reaction is what's going to indicate that the redox reaction has occurred. So really what we're going to see is we're going to learn how to calculate oxidation numbers, and then we're going to apply that in the reaction. So when that oxidation number changes, that's what's going to tell us it was a redox reaction. So the hierarchy and the rules for assigning oxidation numbers must add up to the charge on the molecule, the formula unit, or the ion. Okay, so they don't have to be neutral. They can have an overall charge. It's just that all of the oxidation numbers together have to equal that charge. Atoms of free elements have oxidation numbers of 0. So if it's an element by itself, like silver by itself, would have an oxidation number of 0. If it's a diatomic, chlorine gas, Cl2, its oxidation number 0. So whenever it's in its elemental state, it's a 0. Metals in groups 1A, 2A, and aluminum have +1, +2, and +3 oxidation numbers respectively. So in other words, all the metals in group 1A are going to be +1. All the metals in group 2A are going to be +2. Only aluminum is a guaranteed +3. So you can't say group 3A is all +3. Only aluminum is a guarantee. Gallium and everything below it is going to have 2 potential oxidation numbers. And so you'll have to calculate which one you're dealing with based upon these rules. Hydrogen and fluorine in compounds have +1 and -1 oxidation numbers respectively. So hydrogen is always going to be a +1 and fluorine is always going to be a -1. Oxygen has a -2 oxidation number. Excuse me. Now, oxygen is not always a -2. But it's typically going to be a -2. If you have a peroxide, so H2O2 or K2O2, 2 common peroxides, then oxygen will be a -1. Group 7A elements all have a -1 oxidation number. Group 6A have -2 oxidation numbers. 5A, typically -3 oxidations. When there is a conflict between 2 of these rules or an ambiguity in assigning an oxidation number, apply the rule with lower oxidation number and ignore conflicting rule. That sounds crazy, but we're going to see some examples. The oxidation state used interchangeably with oxidation number. So whether I say oxidation state or oxidation number, what we're looking for is the oxidation number. Okay, tomatoes, tomatoes. This is going to indicate the charge on monatomic ions. In other words, iron 3 would be an oxidation state. It means iron has a +3 oxidation number. Hopefully that made sense. Okay, so it's interchangeable. Whether you say iron in its iron 3 oxidation state or oxidation number, it's interchangeable. All right, so how do we assign them then? Well, here's Li2O. So for lithium, we know we have 2 atoms. They're going to be +1, which means we have a +2 total charge. The oxygen, we only have 1. Oxygen is typically a -2. And then, of course, we sum those up and we get 0. Okay, so it's very easy to do, not tough at all here. +2 - 2 equals 0. So the charges are balanced to equal 0 as well. CO2. Here we have carbon. We have 1 atom times X. There's no rules for carbon, so we don't know what carbon is. However, we know that oxygen has 2 atoms and it's a -2. That gives us a total of -4. Now we know the sum needs to equal 0. Therefore, X must equal +4. Carbon then has a +4 oxidation state. Easy peasy lemon squeezy, I'm hoping. All right, your learning check then. Assign oxidation numbers to all atoms, and in this example, so here's the perchlorate, ClO4 with an overall -1. So a little bit of a caveat there. I'm going to give you a moment here. So we'll do a little pause. All right, so you had a pause. Now, we know that oxygen has 4 atoms. This is not a peroxide, which means the oxygen's a -2. That gives us a total of -8. The chlorine, we have 1 of them, and it should be a -1. That means that must equal -1. If I sum this up, though, I need to have a -1 charge because the polyatomic has a -1 charge. So now we've run into a conflict. This is going to violate rule number 1. Rule number 5 for oxygen comes before rule number 6 for halogens. So that means the oxygen gets to keep its -2. The chlorine then becomes an X, and the total has to equal -1. That means that X then has to equal +7, and that seems really strange, but that's the way these rules work. So oxygen is always going to be a -2. We know the overall for the polyatomic has to be a -1. That means we have -8 in the oxygen, and the chlorine has to add up to get us to a -1, which means it has to be a +7. Now, if the perchlorate breaks apart and the chlorine becomes a chloride, that is going to be our oxidation reduction reaction. All right, so assign the oxidation states to all the atoms. Here's magnesium dichromate. So again, I'll give you a pause. We know that magnesium has to be a +2. We know oxygen has to be a -2, and we don't know what chromium is. So chromium is an X. We know the whole thing has to equal 0. So +2 plus 2 times X, because we have 2 chromiums, plus 7 times -2, all has to equal 0. So 2X minus 12 equals 0. Then X equals +3. Chromium then is oxidation number of +3. That's not mathematically making sense, is it? Because that would be 3 times 2 is 6. 6 minus 12 is not 0. Where did they make their mistake? So we have 14. 14 plus 2. That's where the 12 came from. Ah. All right, so here chromium can't be +3, right? So 2x, of course, equals 12. Then x equals not +3, but plus 6. Okay. All right, how about KMnO4? So K here is going to be plus 1, oxygen is going to be minus 2, and now the manganese is going to equal X. So plus 1 plus X plus 4 times negative 2 all has to equal 0. Let's see if they got this one right. Now I'm a little apprehensive. So here we have 4 times 2 gives us negative 8 plus 1. So we're going to have 7. So it's going to be X with a negative 7. Therefore, X has to equal 7. So here manganese then would have a charge of plus 7. All right. What is the oxidation number of each atom in H3PO4? Of course, here's your pause. So we'll go with the rules here. We know oxygen should be a negative 2. We know hydrogens should all be plus 1s. So we have negative 2 times 4 is negative 8 plus 3. All right. So that means we should have a phosphorus with plus 5. And so that's going to be E. And again, positive 1 for the hydrogens, minus 2 for the oxygens. The phosphorus then has to be plus 5. All right, what is the oxidation number of each atom in sodium chlorate? Uh-oh, now you have to know your naming. Here are your options. What is sodium chlorate? How many oxygens? Because that's going to be the key, right? So it should have been A. And again, if you've got this right, that's because you knew it was NaClO3, right? Hopefully you went and looked it up if you weren't sure. Again, your test will be online, so obviously you can keep naming rules around you in your notes. But anyway, you had to come up with the formula. So at this point, we know that the sodium is going to be plus 1 because it's going to be in group 1A. We know the oxygen here is going to be a minus 2 because it is not a peroxide. We get negative 2 times 3 gives us negative 6 plus 1 gives us a negative 5. So the chlorine then, oddly enough, has to be plus 5. All right. What are the oxidation numbers of sodium and iodine in potassium triiodide? Here are your options. There was your pause. Now this one's going to seem a little strange, right? So potassium is a group 1A metal. It's going to be a plus 1. No options there. It's one of the first rules we have. Iodine should be a minus 1, but we have 3 of them. And the whole thing has to equal 0. So obviously the iodine cannot be a minus 1, because if it were, then we'd have plus 1 minus 3 equaling 0, and that can't happen. So the iodine here then, strangely enough, will have a minus 1/3 oxidation number. Okay, so we know the potassium had to be plus 1. We had 3 iodines, but the total has to be a negative 1. Therefore, it had to be a third. So oxidation numbers can be fractions because they represent an average number of excess electrons, or a lack thereof, on the atoms. In this case, 1 extra electron on the 3 iodine atoms. Okay, so it's all based on the averaging for the electrons themselves. All right, so that's how we calculate oxidation numbers. We'll take this as a breaking point right here. So this will be segment 1. And then next we'll get into segment 2, where we're going to look at how to redefine those oxidation and reduction numbers in terms of the oxidation number. So we'll start to get into those reactions. All right, so stay tuned.